So today the last lecture would be on love and heat. So I guess the title is pretty appropriate for the current week as well. So I don't think it needs further mention. So, but you should not take it literally, of course, because we are discussing something different. So we start with the question that what causes tides on Earth? So what will be your answer? Right? Come on, tell me. Tides on Earth. Who causes tides on Earth? Huh? Due to moon. Sun, are you sure? I mean, whose contribution is most? Moon, right? So why? Whose force is strong? Huh? Whose force, gravitational force on Earth is stronger? Moon or sun? Huh? So how many moon, how many sun? Huh? Moon, right? Yeah. So then Earth should move around moon, right? Why is it moving around sun? Yeah. So it should be sun whose gravitational pull is stronger, obviously. Right? Then why is tide caused by moon? It should be due to sun. I mean, if you have been at my earlier lectures, you know the answer. I mean, you may know it even otherwise, but anyway. So the answer is it's not the force that causes tide, it's the gradient of the force that causes tide. And gradient of the force is larger for the moon than the sun, and hence tide is predominantly caused by the moon, not by sun. So this also tells you another interesting fact about gravity, and this is intimately connected with the equivalence principle. So what is force? Force is nothing but the gradient of the potential, and that tide is gradient of the force. So that means we have double derivative of the potential. So tide is related to double derivative of the potential, right? Now at the same time, we know that gravity is described by metric, and in the Newtonian limit, metric is nothing but the potential. The GT component of the metric, for example, is equal to 1 plus 2 phi, where phi is the gravitational potential. So double derivative of the potential translates to double derivative of the metric, and you know what is double derivative of a metric, right? It's Riemann. And Riemann being non-zero tells you that you are really living in a gravitational field. So that means if you have tides, that tells you that you are actually in a gravitational field. If you do not have tides, then you are living in a non-inertial frame of reference, but there is no gravity. Because gravity means there is a non-zero Riemann, and whenever you have non-zero Riemann, you will definitely have tides associated with it. So therefore, tides are extremely important. It tells you that really there is gravity. Secondly, suppose the seas on Earth are not made out of salty water, but of fresh lime soda, right? Then one consequence would be would have drunk them all up by now. But other than that, of course, the deformation that moon is going to cause will also be different. Right, because water and lime soda, they are definitely different fluids with different viscosity and so on and so forth. So that means suppose there is some extraterrestrial, some alien out there which is looking at Earth by their super telescope and finding how much the moon is causing tidal deformation, the height, for example, and they found that the height is 16 centimeter. And they deducted, in principle, can deduct that Earth is actually made out of water and not of lime soda. And this is exactly the same thing we are doing by sitting here on Earth. We are saying that neutron stars are made out of what kind of material? This physics is exactly the same. So we have two neutron stars which are moving around each other, and neutron stars, as you know, are made out of some material, some fluid, say for example. And due to tidal deformation, which is the tides that we see on Earth, which is what is referred to as tidal deformation, there would be some deformation to the surface of the moon and so on and so forth. And this deformation depends on what the neutron star is made out of. So therefore, if you can measure this deformation, you will have a good idea about the constituent of a neutron star, and that is what people use in order to constrain the constituent of neutron star, or in other words, the equation of state of neutron star. The question that I will predominantly be asking is what a black hole is made out of. Suppose you have a black hole and you have another black hole, another star, whatever, and then this is also going to tidally deform the, right. So what is the amount of deformation, if you can calculate it explicitly, and how much is the deformation, and from measuring that deformation, what can you comment about the constituent of a black hole, if you can say anything. So this title actually should not be this. This title should be slightly different. It should be tidal love number and tidal heating. So you see, I have picked the two words from there. Okay. So now the reason this is called tidal love number has nothing to do with the word love, because this deformation was first measured by a British astronomer whose name was Love. So that's why in his name this number, which sort of characterizes the deformation of an object under external tidal field, has been referred to as the tidal love number. This is a number. If the number is small, that means your deformation is smaller. If the number is large, that means the deformation is larger. So this quantifies how much deformed an object can become when it is placed under an external tidal field. Now, why this tidal deformation is important? Because in gravitational wave, as I said, we have these two black holes, or a black hole and another compact object. They are moving around each other. So they are inspiraling around each other, just like Earth and Moon are orbiting. I mean, it's not a very good analogy, but typical. You can just as a thinking of the system. So in that context, you have these two bodies which are in close contact. So one is pulling the other. So there is a tidal field, and that tidal field is going to cause some deformation. Like if you have seen the movie Interstellar, then there is a very old black hole Gargantuum, and then there is another star planet which is circling around it, and there are these huge waves which are caused due to the tidal forces. So we want to find out what is the height of those waves, for example, which would be caused by the tidal force. But the only difference is we are looking at two black holes and not looking at neutron stars, or any stars for that matter. However, the analysis that I will try to chalk upon, I will not get into details because we are all at the end of our day. So therefore, I will be less mathematical but more qualitative arguments would be there. So let us start with the Newtonian case. So what do you expect? So as I said, your GTT is something like 1 plus 2 phi with a minus sign, where phi is your gravitational potential, or you can revert it and write phi as half of 1 plus GTT with a minus sign, right? And both are equivalent. Now, given any gravitational potential, suppose initially when there was no tidal field, the object was spherically symmetric, because we are only discussing spherical symmetric situation. Then what is the Newtonian potential? It is simply mass of the object divided by the radial distance. So I would have a term which is minus m over r, right? Now you have another object which is nearby, which is causing the tidal field, and as a consequence the object is deformed. So what you do when you try to compute the gravitational potential of a deformed object? What is the procedure called? multiple expansion, right? Just like in electrostatics, if you have a deformed charge distribution, you do a multiple expansion of the electrostatic potential. Here also you do multiple expansion. So in multiple expansion, what happens? First you have the monopole term, which you already have here, m over r. Then you have a dipole term, and then you have a quadrupole term. Now for gravity, dipole term does not exist. Why? Because you can always choose your origin to be the center of mass, and then the dipole just goes away. So that is why in gravity you do not see dipole radiation, which you would see in the context of electromagnetism. So the next non-trivial term starts at a quadrupolar level. So the next term would read something like this. There would be a Qij divided by r cube Ni Nj delta Ij. There can be some factors of 2/3 or 1/3, but I mean this is the structure that you will have. This is the quadrupole moment Qij. The Ni corresponds to xi over r. So these are like unit vectors per se, and delta ij is the Kronecker delta which is present. The Qij has the property that it is symmetric and as well as it is stressless, right? But this is not all, because we want to find out gravitational potential. Now remember, I have two bodies, one body which is being deformed and another body which is deforming. So that means this is the contribution coming from the body which is getting deformed. So I should also add to it a contribution coming from the body which is causing the deformation, right? So how do I determine that? As we mentioned that the tidal field is related to double derivative of the potential. So it is del 2 phi, del xi, del xj. Right, so I take the gravitational potential, first derivative is giving me the force, the second derivative is giving me the tidal field. Now tidal field is generally what is known as a tensor, so that's why we write it as Eij. So therefore, now if you assume that the tidal field is constant over the extent of the body, then you can easily integrate this equation and you will find that this will simply become half Eij xi xj. So this is the contribution coming from the deformed object and this is the contribution coming, this is the cause of deformation. Correct? So I have a neat separation between the two parts, right everyone? So if I set Eij equal to 0, means there is no deformation, no tidal field, then my Qij should also vanish. So if you take moon away from earth, then there is no tide. I mean, of course there would be some tide due to sun, but predominantly speaking, there would be no Qij which is present. So this means just like in harmonic oscillator, if there is no force, then there is no displacement. So therefore, force and displacement are found to be linearly related in the case of harmonic oscillator. Similarly, Eij and Qij at linear order, they must be proportional to each other. Because if you do not have Eij, you do not have Qij, and that's it. So that means Qij must be proportional to Eij. It can also depend on square of Eij, derivative of Eij and so on and so forth. But I mean at leading order approximation, we can say that Qij is lambda times Eij. Next, yes. XYZ. XYZ. Yeah, one of them, see this is one object, this is other, you are measuring it from some other location. Yeah. Or you can think of it exactly, this would be that. From that origin, you have a distribution. So like Qij, how do you define that Qij? It would be integrated over rho xi prime xj prime minus 1/3 delta ij r prime. where r prime corresponds to points within that mass distribution. Yes. So this x corresponds to your field point. Right. So you have two things when you do multiple moment. One is the where are you measuring the potential, and then you have this qij. So if you want, I can give you the definition of qij. So qij will be defined as integral d3x prime rho x prime, and then you have xi prime xj prime minus 1/3 delta ij r prime square. So no, this is just integral over the deformed object. Yes, so as I said, this part just comes from the deformed object, and this comes from the object which is causing deformation. This Eij is something that I have assumed to be almost constant. So that is why it's like integrating this equation to obtain Eij xi xj. Right. So you can probably make another Taylor series expansion and have derivatives of Eij and so on and so forth, but they will all be higher order corrections. So therefore, I am not going into all of that. The main is this relation that we have between Qij and Eij. Now you see that dimensional argument, Qij must have a dimension of length cube, because potential must be dimensionless. Mass has a dimension of length in the system of units that we are considering. So Qij must have a dimension of length cube. Eij on the other hand must have a dimension of inverse of length square, so that it is dimensionless. Then from here you see that lambda should have a dimension of length to the power 5, because Qij has a dimension of length cube and Eij has a dimension of 1 by length square. So in physics normally we talk about dimensionless numbers. So that suggests to define this guy which is called K2 as lambda r to the minus 5. Normally there is a factor of 3 by 2 which is associated for just conventional purposes. So this K2 is dimensionless because lambda has a dimension of length to the 5. I have multiplied with something which is length to the minus 5. So this K2 is dimensionless. So this K2 is what is called as the tidal love number, or TLN for short. Right. Now you will ask, what is R? Right? What is that length scale? So if you are doing black hole physics, then R should correspond to the horizon size of the black hole, which is 2m for Schwarzschild. If you are doing neutron star, then R should correspond to radius of the neutron star, and so on and so forth. So generally, whenever you are dealing with a problem, there would be some characteristic length scale associated with it, and that is what is going to sit there. There are cases where things can be ambiguous. For example, if you have a black hole placed in a dark matter halo, then there are more than one characteristic length scale, so it is not very clear which one to pick. But we are not going to discuss any of these situations here. So for us, it is either black hole or neutron star. So that means I have a characteristic length scale, which is either the horizon size of the black hole or radius of the neutron star. And that gives me R. And then this K2 is dimensionless. Now what is this 2 signifying? This 2 is signifying that I am only working with the quadrupolar deformation, which corresponds to L equal to 2 in the multipole expansion. In principle, I can have L equal to 3, L equal to 4, L equal to 5, all the higher multipoles would be present, and they would also produce a similar love numbers. So there would be K3 corresponding to L equal to 3, the octopole, then L equal to 4 would give me K4, there would be K5 and so on and so forth. So you will have a bunch of tidal love numbers associated with the deformation of any object. The quadrupole one is the most dominant, so that's why people generally talk about the L equal to 2 quadrupolar deformation, K2, but in principle you can have K3, K4, K5 and so on and so forth. Right? It makes sense to everyone? Okay. But this is Newtonian. So for black hole, as you know, that Newtonian physics cannot be applied. So we have to resort to general relativistic calculation. So what should we do? We should study gravitational perturbation of a Schwarzschild black hole. Why it is perturbation? Because there is a object which is far away and I have a black hole here. So that means the black hole is getting perturbed due to the external field. So that also has to be studied by the gravitational perturbation that we were discussing in the previous class. But there are some differences. Because earlier what we are trying to find out was the QNMs, which are the eigenvalues of the Regge-Wheeler function, which are some master function satisfying some equation. But here we are not interested in that. So if you see carefully, what we are interested in is the perturbation of the GTT component of the metric. Now that is not my psi Regge-Wheeler, which I had defined before, or psi Zerilli, which I had defined. This is a particular metric component that I am interested in. So that means I cannot use the previous results that we have derived for Regge-Wheeler and Zerilli, but rather we have to use perturbation equations for these objects. And that is where things are slightly different than how you deal the quasi-normal mode problem and makes it slightly different from the TLN. So let me go to this perturbation then. So what I said, there are two branches. One is axial, sorry, and the other one is polar. Right? So axial had 2 degrees of freedom and polar has 4 degrees of freedom. Correct? So for axial I have delta G T theta, delta G T phi, and there would be delta G R theta as well as delta G R phi. So this would be denoted as H0, this would be denoted as H1. Similarly for the polar, I will have delta G TT, I will have delta G TR, I will have delta G RR as well as delta G theta theta. This will be denoted as H0, this will be H1, this is H2 and this is K. And finally, you also have delta G phi phi, but that is nothing but delta G theta theta into sine square theta. So these are the 2 axial perturbations and these are the 4 polar perturbations. Just to remind you, there is no analog of axial tidal love numbers in the Newtonian case. So this K2 that we derived, as you can see, comes from the GTT component. That means it effectively comes from this H0 by solving the equation for H0. So that is why these are referred to as the electric or polar TLN. There would be a similar love number and that is why these are denoted as E. There would be similar set of love numbers coming from the axial sector and those are called the magnetic tidal love numbers, which have again no analog in Newtonian gravity. And the magnetic love number comes from solving this H0 equation. Right? Is my argument clear? So I have 4 variables. I will show you what happens in this case. So among those 4, what I am interested in is this H0 and its solution, and from that solution I want to determine my electric type tidal love numbers. On the axial sector, I have 2 unknowns, H0 and H1. I want to solve for H0 and hence determine the corresponding magnetic type tidal love numbers. Now normally the calculation that people does are for the static case. So let me put it here. So what we will do, we will discuss the case of static tidal love numbers. Even though I will say that static tidal love number is really a misnomer, because you have 2 black holes which are moving around each other. So there is nothing which is static, right? It's really a dynamical process. So saying that we are doing static tidal love number is a bit of a misnomer, right? If you are from Bengal, then you will know there is a thing calling Sonar Pathor which is very similar to the static tidal love number. But anyway, people try to compute the static tidal love number because they are simpler to calculate, and I will try to give a hint at the end that how do you calculate the dynamical tidal love number, for example. Now, static means that you should set your omega to 0. Why? Because static means all time derivative has to be set to 0, and as you know, your time dependence always comes as e to the power minus I omega t. So that means if you set omega equal to 0, all the time derivatives are automatically set to 0. So therefore, all the static calculations are done with omega equal to 0 substituted in the perturbation equation. When you put omega equal to 0, the first thing that happens is that your H1 goes to 0, which you can show that by manipulating this equation, that H1 will be proportional to omega, and whenever omega vanishes, your H1 goes to 0. So that means you really do not have to worry about 4 independent quantities, you only have to deal with 3 independent quantities, H0, H2 and K. Yes.
Which equation are we solving?
Oh, sure. So we are solving this equation, the perturbed Einstein's equation. Okay. Same equations, but in QNM what do? We do not solve for H0. What we do, and we do not set omega to 0, because if I set omega to 0, then there is nothing. See, you are trying to find out in quantum mechanics your energy eigenvalues. If you set E equal to 0, then what is to find, right? So therefore, you do not set omega to 0, first thing. Second is, you have these 4 variables. In QNM, you keep all of them. But what you can do, which is something I am going to do right now, is that you can show H0 is same as H2. That comes from the theta and phi equations. So then you have 3 unknowns, H0 equal to H2, which is capital H, H1 and K. You do not set H1 to 0. And afterwards, what happens is that you can try to find out a linear combination of H1 and K, which is called the Zerili function. That gives you that master second order differential equation. Similarly here, you have H0 and H1. You take a combination of H1, which I mentioned, some DDR of H1 by R with some I omega by R outside. So that is what is called the Rege-Wheeler function, and that you use to solve your QNM problem. The reason you do that is because you can reduce it to a Schrodinger-like equation and use all the machinery that you know from quantum mechanics in solving them. But I mean, even if you do not do that, there are ways to solve them, but let us not get into that. Here the physics is different. Here we are not interested in the QNM. What we are interested in is how much information in the GTT component. So I am not interested in omegas. I am interested to know that if I have a perturbation, how much is the GTT component different from the Schwarzschild value. Because if you put this GTT for Schwarzschild, you will find that the leading order term would be m over r, which is present. Because what is GTT for Schwarzschild? Minus 1 plus 2m over r. That minus 1 plus 1 gives you 0. So you have minus 2m over r, and then there is a minus half. So modulo the sign, you get m over r, which is exactly what you expect for Schwarzschild. But when you bring in a second body, then your GTT component is not 1 minus 2m over r. There would be corrections. What is the correction? The correction is precisely this quantity H0, because this H0 measures what is the perturbation in the GTT component. So if you can solve for H0, you know what is Qij and what is Eij. If you know what is Qij and Eij, you can determine what is lambda. If you know lambda, you can determine K2. Right? Clear? Okay. Any confusion? Great. So what I was, yes. I will come back to it. Yeah, that I have not discussed yet. Okay. After writing down that equation, I will get back to So I have H0, H1, H2 and K, and as I said, when omega is 0, my H1 is also 0, and you have this thing which is delta G theta theta minus delta G phi phi. This is also 0, which you can show for any perfect fluid model. Actually, for any isotropic, even for non-isotropic case, there would be cases where this would be 0. This is the case where we can do things actually analytically. There can be cases where this is not 0, but that is not in our hand. I mean, they are very difficult to solve. So this, as you can show, implies H0 equal to H2. This is something that you can prove. Right? For that, you have to take my word, because these are notoriously long expressions, so I do not want to get into that. Okay, I mean, what are this exact form of these expressions? You can find in some references, like there is a paper by Niels Anderson in 1999 which does this. So you can look at that, or there are also recent papers which discusses this, but I will not do it over here. So you can prove that H0 equal to H2, and generally people say that this is same as H. So after you have done that, that means you are left with only two variables, H and K. Because H1 is 0, H0 is same as H2, which is same as H. So I have H and I have K. Right? Yes. Correct. Yes.
So here we are setting omega equals to 0.
Yes.
And this is, and you were saying that we still have it as an exponential of I omega t.
No, I am not saying. There is no t part, there is no time dependence, it is static.
Yeah, but omega equals to 0 is set where, I think.
In the equations. So for example, whenever you are there would be like 4 equations, one for H0, one for H1, one for H2, one for K. Those equations will involve del T of H0, say for example, right? Now, and as you know that neither of the background depends on time. So therefore, del T, there would be no time dependence which is multiplying H0, because H0 is the first order perturbation. So what should multiply H0 is the 0th order term, and 0th order term has no time dependence. So there is no time dependent term multiplying H0. Time dependence can only come from such derivatives. So therefore, if you write H0 as e to the minus I omega t and set omega to 0, that is equivalent to setting del T to be 0. Correct? Okay. Okay. So as I was saying, I have only capital H and capital K, which are the two unknowns to solve for. Now what you can show is that this capital K can be completely expressed in terms of capital H from the equations. So that means if you know what is H, you will know what is K, because K is determined entirely in terms of H and derivative of H. So that means in the polar sector, ultimately what you need is a equation for H. This is all that you need, because if you have an equation for H, then you can solve it to get H. After you know H, you can plug that in to get K, and if you know H, you know what is delta G Tt, what is delta G Rr. If you know delta G Tt, then you can plug that in and determine what is Qij and what is Eij, and then you can determine what is lambda. Right? Fine, everybody? Are you with me or no? On the axial sector, on the other hand, what you can show is that in the omega equal to 0 limit, H1 goes to 0. Just like here, capital H1 goes to 0, here your small h1 is 0. And then you just have a single differential equation for H0. So what you do then in this context of love number, you either solve for an equation of capital H if you want the electric type tidal love numbers, or you solve an equation for H0 if you want to solve the axial type tidal love numbers. And then you use appropriate boundary condition that Shubhadeep was asking in order to get the final answer. right? Fine. So what we'll do it for the polar case, because that will illustrate whatever we are going to say, and the axial case, I mean, if you want, I can suggest you some reference where you can look it up. Yeah.
Can this electric and magnetic pattern are this related to electric type and magnetic type and mass type and current type multiple?
Exactly. Yes, of course. So this would be current type, that would be mass type. Fine. Okay. So let me move on then. So where should I write the equation? Okay, good. So the equation for H is something like that. So let me remind me, because I do not remember it. Where is it? Yeah. So this is the equation that you have, which is H double prime. I will explain what it is. So this is the equation where x is, so I am doing it for Schwarzschild. You can see where the 6 comes from. 6 comes from L into L plus 1, because if you put L equal to 2, it is 2 into 2 plus 1, 3, which gives you 6. So if you want to do it for generic values of L, you have to change that 6 to L into L plus 1 and plug in whatever is your favorite L value. These 4 and other things, they come from rescaling of mass and things like that. X is, as I said, is r by m minus 1. This derivative prime denotes derivative with respect to x. This differential equation, I am not sure if you are familiar with it, but this is nothing but the associated Legendre polynomial. And the solution for H is C1 PL2, I think it is r by m minus 1, or it is 1 plus 2x actually. So let me put it in terms of x. It is 1 plus 2x plus C2 QL2 of 1 plus 2x, where C1 and C2 are the arbitrary constants of integration that is associated with the second order differential equation. Okay, and 1 plus 2x, you can just plug that in and determine what it is. Fine? Clear? Yes. Is there any question? Now comes, how do I determine C1 and C2? Right? That is the main point. So for that, what you do, you take the limit when x tends to infinity. Now this is a very tricky limit. So let me explain what is being meant by x tending to infinity. So the physics is as follows. You have an object which is deformed, and you have another object which is here, which is causing the deformation, right? Now, this is a bad place to put it. Let me put it here. Now suppose I am going to this region. Suppose, right? There, none of this actually holds, because the inside of that region is a two-body problem. It's not a single body problem as we are addressing. Because you remember what I am doing, I have a single black hole which I am perturbing. I am not considering two black hole being perturbed or something. So that means this x tends to infinity should actually refer to a region which is here, such that it is far away from the first object. It is also far away from the second object, such that our approximation that we can treat the tidal field over that region due to this object makes sense. Let me again repeat. So suppose you are doing Earth and Moon. This x tends to infinity means you are far away from Earth, but not as far away as Jupiter. You are in between Earth and Moon, so that Moon is also far away from you, Earth is also far away from you, so that you can work out things within this approximation. This region where this approximation is valid is what is called an intermediate region. So normally in gravitational wave or physics, this type of research, whenever you do, your regions are divided into three parts. So let me discuss that because it may appear at various places. One part which is close to the horizon is what is referred to as near zone. Okay. So these are generally characterized by the definition that the frequency with which you are interested times the mass of the object is much smaller than 1, and the frequency and the radius of your interest is also smaller compared to 1. This is what is referred to as a near zone, where you are near the black hole. Then you have what is called the intermediate zone. Okay. And then you have what is called the far zone. So you see another approach to compute QNM. So let me tell you how do you do that for anything. So you solve it in the near zone. You know how to solve it because you are assuming that you are close to the horizon and things like that. So you solve it here. Now that solution will depend on R. Now you take a limit when R goes to infinity. That does not mean you are going to an infinity over there. That simply means you are going to the intermediate zone because your solution is only valid when you are close to this object. Then you also solve it in the far zone, and that you take limit when R goes to 0. That does not mean you are going towards that because this solution is only valid when R is much away from the black hole. It is actually valid in the intermediate zone, and you match the two where both the solutions are valid. So here we do not have a far zone because we have a second body which is present, but we do have an intermediate zone, and so that means the solution which I am presenting, and by extending to infinity, what I literally mean is x is much larger than the size of the object because x is related to r over m. When r is much greater than m, that means I am far away from the object which is getting deformed, and then I am in the intermediate zone. But I can never cross it and go to the other side because then the whole calculation loses its meaning. Is that clear? It can be anywhere in between. Yeah, the only condition is R has to be much larger than M, and also it has to be, well within the tidal field. Yes.
So I understand this part, like if all this the formalism such that like we have the intermediate zone and solving for that, but the waves are being observed by
Correct.
By the observer sitting at
Correct.
So how do you connect those two then?
Yeah, that is secondary. So first what I want to find out is what are the tidal love number. Then the next question that you ask is how is the tidal love number sitting in the gravitational wave waveform, because that is what you are going to observe, right? That will come from some of this post-Newtonian calculation and all that. So that I am not doing here. For example, you can add a point particle action and add this EIJ kind of a term which you do in effective field theory approach, and then you work out and see at which post-Newtonian order it appears. Right. So that is a separate question which we are not addressing. Our aim is to find out what are this quantity which are K2. Okay. So let me proceed then. So now when you take x tends to infinity and both of them has a well behaved asymptotic behavior, what you can show is that the h, if I write infinity, which is a misnomer, it would be C1, and I think this is the, so it would be R over M whole square, and this would be C2 M over R with some factors, but that again is not important here. So this PL2 is going to grow and this QL is going to decay. So you will have contribution from C1 and C2. Correct? Fine? Everyone? Now comes the first thing. So this H, as I said, is the perturbation to GTT. Perturbation to GTT means whatever is addition to the m over r. Now what is addition to m over r? 1 over r cube, which is qij, r square, which is eij, right? 1 over r cube, which is C2, r square, which is C1. So this is exactly what I had written from the Newtonian point of view, which is exactly what your GR's asymptotic limit also gives you. So that means you can relate your C1 to be your eij, and you can relate your C2, which is 1 over r cube, to your qij. Then what is your lambda? Is the ratio between q and I. So which is C2 divided by C1, right? See if this is fine. Great. So then my job is done. So I have a lambda which is C2 by C1. Right? But now we will jump up and down and say, well, what have we achieved? C2 and C1 are both unknown, so their ratio is also unknown, right? So we need something more in order to find them out. So that more for a black hole is the condition that my perturbation should be regular at the horizon, which is a pretty natural assumption, right? If my perturbation is not regular at the horizon, then even the horizon itself is not well defined, so I do not know what I am perturbing with. So I do not expect, my full black hole to blow away just because I have added a tiny perturbation. Correct? So I need my H to be well behaved when R goes to 2m, which corresponds to x tending to 1 and things like that. Okay. Now the problem is, when you do that expansion over here, what you find is that this PL2 is perfectly well behaved. Actually, this PL2 goes as R into R minus 2m, from where you actually get the R square. But the QL2 has a term which is, it actually has two terms. So I need some more space to write. So let me do it here. So this QL2, that has one term which is R minus 2m log of R minus 2m, and then another term which is a function of R divided by R minus 2m. So you can work out what is the explicit form for QL2, and it will have a structure like this. Actually it will be for Q22, because we are interested in L equal to 2. So first term is not of a concern, because x log x is finite when x goes to 0, but the concern is the second term, because you have 1 over R minus 2m, which tells you that if you want regularity at the horizon, you cannot have Q22 term. Now if you cannot have Q22 term, the boundary condition tells you that your C2 must be 0, and if your C2 is 0, that tells you that your lambda should be 0, which in turn means that K2 is 0. So in one word, this tells you that static TLNs of Schwarzschild black hole is 0. Okay, so this is one of the most important result in the, I believe so, in the gravitational wave literature, that black holes in GR have 0 tidal love number. That means you cannot deform a black hole, at least by linear perturbation analysis. Right? Clear? So therefore, this is a distinctive test for black hole. Why? Suppose now that I am not interested in black hole, but I am interested in an exotic compact object, horizonless compact object, whatever, ultra compact object, whatever you choose. Then the boundary condition would rather be that my H, which is this, should be regular at or actually what people do is, so let me show you the result for a perfectly reflecting case. So let us assume that instead of a black hole which absorbs everything, let us have a star which reflects everything near r equal to 2m, right, as I mentioned. So perfect reflection tells you that H has to vanish, and if H vanishes, then you can determine your ratio C2 over C1 by just the ratio of Q and P evaluated at the surface of the exotic compact object, correct? And this exotic compact object is located where? At r equal to 2m plus epsilon. So if epsilon is 0, you get back black hole. If epsilon is non-zero but some small number, you get an object which is very compact but not black hole, because you have not touched the surface r equal to 2m, correct? So you need to find out what is your q to 2, correct? And you also need to find out what is your p. Now what happens is that you see there is a log of r minus 2m, which gives rise to a term which is log of epsilon. And what you can show, the other 1 by epsilon terms, they can actually cancel, and your k2 will turn out to be 1 by, there will be some numerical factor b log epsilon. This is for ECO, and K2E is 0 for black hole. So this log epsilon scaling is something which is extremely peculiar, and it only happens for this exotic compact object. You see that when you take epsilon tending to 0 limit, which is your black hole limit, then your log epsilon diverges and you get back the result for black hole, which is K2E equal to 0. So therefore, just as for Q and M, the black hole would have this characteristic ring down frequency. So it starts with a high oscillation, then it decays exponentially and goes to 0. For echo, after the oscillation dies down, there can be other oscillations coming at later times, which is something, as I said, is a telltale signature that it's not a black hole. Similarly, if you see that these love numbers, however way they are measured, turns out to be non-zero and has some sort of a logarithmic scaling with epsilon, then that is again a signature that this is not a black hole, because for black hole it must be equal to 0. Does that make sense to all of you? Okay, what is that? 6. Okay, that is what I am going to come to now. Yeah. So, the static limit, yes. Yeah, yes.
Sorry, so using this TLNs, you also calculate the height of the tidal waves.
What is TLN? Oh, sorry, yeah, sure.
You calculate the height of the tidal waves.
Yeah, height in the sense that this tells you how much is the deformation, which is like telling you what is the height of this wave. So if the deformation is small, then of course that means the tides are small. If the deformation is large, that means tide is large. So actually we do not predict what is the height. What we predict is what the material that star or whatever is made out of.
Okay. So K2 being 0 for static black holes, so it means we are unable to calculate that, or?
No, it just means there is no tide. Because there is no deformation. You have a black hole, it remains as it is. There is one catch, I did not want to get into that. So there is something called superficial love number in contrast to this electric love number. You remember we computed this by computing the deformation in the gravitational potential. So this being 0 means if you are looking at a gravitational potential outside that object, then that is the same as that of a monopole. But if you are really asking whether the surface itself is deformed, then that is computed by something called the superficial love number, which has a different definition. That actually turns out to be non-zero. So the black hole is deformed per se, but its gravitational potential is behaving as if it is a monopole. Okay. So this is slightly weird even to me, but that's how this field stands. Okay, so without further ado, let me come back to the other thing. So the main question that people asked after this one is what happens for Kerr black hole, and yes, no.
Because you mentioned it, I wanted to
Sure. Okay, so sure. So in the Newtonian case, the way you define it, you say that I have the radius of the object is r, and you say that r goes to r plus delta r. So you then expand this delta r and try to measure what is the deformation of the radius. Now the point is, in the relativistic context, of course radius has no meaning. So what people do, they compute the curvature of the two surface. So you have this, this, where is the metric? Oh, the metric is not here. You have r squared d omega square. So that defines for you a two surface. You compute what is the scalar curvature of the two surface before and after perturbation. And that you say is a measure of my superficial love number. Now what happens is that when you compute the deformation in the curvature, along with h, it also depends on k. Now if you look at h will never give you a deformation, because at r equal to 2m, if you set this C2 equal to 0, then as I said, PL2 goes as r into r minus 2m. So at r equal to 2m, this h is actually 0. So there is no contribution from h, but k turns out to be non-zero. So that is why the perturbation of the two surface metric, the scalar curvature, that gives you a non-zero result. Now that people uses to define the superficial love number, because in Newtonian limit it relates to this perturbation delta r. But that is the conceptual part, like whether it is really related to the surface deformation or not, that is again. So the point is, in the Newtonian limit, this two surface curvature perturbation is related to change of radius. So it does match with our intuition. Yes, Gaussian curvature, but in general relativistic case, you just can compute that curvature, because this is not a gauge invariant quantity.
If the deformation doesn't imply a rotation, so
it just yes.
Then you just have the electric.
Yeah, so K is also coming from the electric part, right? It's all fully polar.
I mean, the superficial is 0.
For the magnetic is 0, but for the electric it depends on both H and K, because K is also a polar.
Yeah, but if I take a perturbation, it just briefly more. So just.
But there is no time dependence, right? It does not oscillate.
Right.
So it's like saying, like, you have a spherical surface, there can be some deformation with some.
Yeah, but that's what I mean. So that you have to have it something that is not isotropic.
Yes, there has to be theta phi dependence. Yes.
Otherwise, if it's only just blowing up.
Yeah, that is not going to. Yeah, that is true. That is true. And you can see that is why K is coming, because K is related to the theta and phi. So this deformation, non-isotropic nature is hidden inside K. So that is what is causing this to be non-zero. Yes. Superficial. Yes. Yes, absolutely.
Won't that imply that you have monopole modes in the gravitation factor? Because it's not strictly symmetric.
But that is at a perturbation level, right? What would that imply? What is this? Correct. Mm-hmm.
I think that you also have monopolar modes in the gravitation factor.
But why?
Validating in some way Markov's theorem.
But Markov's theorem is only true for, static spherical symmetric configuration. I mean, we have a perturbation which is not spherically symmetric. So why should there be Markov's theorem? Right? Maybe we can talk about it, but I don't think that's an issue. Yes. No, my motivation is to prove black hole has zero tidal love number. Okay, but if you want astrophysical implication, then of course to test. Yeah. Absolutely.
But can you comment on the case of lambda at non-zero? Then why does introducing lambda
Okay, maybe not here. Okay, we can discuss it later on. So lambda, so what he was asking about cosmological constant, so there were some results in which unfortunately or fortunately I was also involved, which shows that if you add lambda, then it gives you a non-zero tidal love number. So his question is why. So the answer partly is to do with the fact that this definition of L gets modified, and as a consequence you will get some correction out of it. But I don't think this is a proper platform to discuss that. We can discuss it later. Okay, next thing that, okay, I think I'm running out of time, but that's okay. I can do tidal heating in my last talk. Okay. Next thing, as I said, is to try to understand what happens for Kerr black hole and what happens in the dynamical situation. Now for Kerr black hole, I will just give you a history, because that Kerr black hole calculation, I can just tell you a final answer and just show how things can be done. So for Kerr black hole, there were initial claims that for slow rotation it should be 0, which was by Poisson and others. Then in 2020, people came up with a more gauge invariant approach, which, as I said, the Newman-Penrose formalism, wild scalar, and so on and so forth. And there was a paper from Latier, Casal, and others, where they argued Kerr black hole has non-zero tidal love number. So people are very excited that, oh, we have something very interesting coming up. Then after 2 months, another paper came in and which says that, look, that is not correct, the interpretation is wrong. Kerr black hole should have 0 tidal love number, right? And then, I mean, people have gone to various other extent, whether it is 0, non-zero, and so on and so forth. But the main point of calculating the love number for Kerr black hole, which is what I will briefly tell you, is to not solve this equation for H and K, because as I said, the rotating case you do not have such, I mean, there are metric perturbations, but they are more difficult to tackle because of the complicated nature of the background metric. What rather you do is that you work with this Teukolsky equation, and these are equations for these quantities which are known as psi 0 and psi 4, and psi 0 and psi 4 are nothing but you take the Weil tensor W alpha beta. So you know what is Weil. So Riemann, if you contract on 2 index, Riemann has 20 independent components. If you contract on 2 index, you get the Ricci tensor, which has 10 independent components. So where are the other 10? The other 10 components are hiding in the Weil tensor, which you can get by subtracting out Ricci scalar as well as Ricci tensor from the Riemann in a certain suitable way. If you contract this with appropriate null vectors, because these are both scalars, we have to contract all the 4 indices, then one of them is called psi 0, one of them is called psi 4. Okay, there are I think psi to 5 of them. So psi 0, psi 4, psi 1, psi 2, psi 3. Psi 1, psi 2, psi 3 does not matter for Kerr, but only psi 0 and psi 4 matters. And you get some differential equation for psi 0 and psi 4, which are called Teukolsky equation. These equations you can solve analytically in the near zone approximation, as I said, assuming frequency to be small, omega z to be small, and the solutions are generally in terms of, say for example, psi 4 can be written in terms of hypergeometric function with some arguments and then b into another hypergeometric function. These hypergeometric arguments can depend on L as well as on omega and so on and so forth. There are 4 arguments. Hypergeometric functions are also well known functions with various limits being beaten to death, just like this PL2, QL2, the associated Legendre polynomial. So what we know is that in the limit sorry, in which I am going to a large distance, one of them behaves as r to the power L and the other one behaves as r to the minus L minus 1. So you see, if you put L equal to 2, you get r square from here. If you put L equal to 2, you get 1 by r cube from here, which is exactly what is written over there. You should have a 1 by r cube fall off and a r square growth for the tidal. So that means even from this expression, the coefficient of r to the L and r to the minus L minus 1 will give you the corresponding expression for the tidal love number. But the problem is, you can see that Tucholsky equation is in general complex. So that is the main problem with Tucholsky's equation, that you get equation which has I omega, for example, present inside. As a consequence, the coefficient that you get here as the coefficient of r to the l and r to the minus l minus 1, they are also complex. Then if you take their ratio, you get something, but that is a complex quantity. So what do you make sense of it? It cannot be, you cannot just say that it is love number, because love number is supposed to be real. So the argument that goes is as follows. So love number corresponds to the conservative part of our system, because if you get away the cause for the tidal deformation, it comes back to its original shape. So love number is a conservative quantity. On the other hand, there is something called tidal heating, which I will discuss, that is related to a dissipative system. So dissipation means it is related to some sort of a time derivative, and time derivative always gives you a factors of I omega, meaning it can lead to complex or imaginary part. So therefore, there the computation goes as follows. You compute the coefficients and their ratio gives you what is called the response function, FLM. The real part of this FLM gives you the tidal love number, because real part means it is conservative, and the imaginary part of it gives you the dissipation. So therefore, you have to compute the real part of FLM, which should be related to your love number. You compute the imaginary part, that gives you the dissipation, right? Now I will briefly talk about the evaluation of this quantity, because this is pretty simple and you should know this, but this is not great. Now it has understood it is me. So let me write it down. So this FLM is, it's a long expression, so it is impossible to keep in mind. So the result is this 3 plus L. Okay, I will make it simpler. There are more complications, but let's not get into that. So this is the form for FLM. The first thing that you will notice, and you will say that, well, this does not make any sense, is this term, gamma of -1 minus 12, which, as I said you before, if L is integer, then this of course diverges, then what is there to do? But the way around this problem is what people advocate as the way of analytic continuation. In the sense, you say that L is not an integer, L is actually a complex number. And at the end of my calculation, I will take the limit where L goes to an integer, and only then everything needs to be proper. I do not care about intermediate steps. Now, how do you take care of this term? You use this famous identity, which is gamma z into gamma 1 minus z, which is pi over sine, it is sine actually, sine pi z. Right? This is the famous gamma function identity, which relates gamma z to gamma 1 minus z. The usefulness is, if you put here gamma -1 minus 12, this would be gamma 2 plus 12, which is pi by sine of 2 pi. So I want gamma -1 minus 12. I have converted that to gamma of 2 plus 12, which is a perfectly well behaved quantity. Then of course I have the sign to take care of, because if L is integer, the sign is going to 0, but that is something we will take care of. Next thing, the next problematic part is this gamma of 2 minus L, because for gravitational perturbation, L is always greater than or equal to 2, and then this is also going to give you a negative contribution. So what you do, you play the same game, that is, you use the same identity over here, and this is going to be useful. So therefore I have gamma of 2 minus L, then this would be what? L plus 1. Is it L plus 1? This is Z. Yeah, it is L plus 1. I'm correct. So pi by sine pi plus pi. Fine, makes sense. It's not a black magic, right? This is honest to God mathematics. This is an identity which, I mean, it should be not very difficult to prove, and then rest of it is easy. Okay. So actually, let me tell you, I mean, there is, yes, L minus 1. Yes, you are correct. And then I am also wrong here. It should be minus pi plus pi L. Okay, so this identity, just for the sake of it, a similar identity also arises when you derive Unruh effect, for example. I mean, thou would know about it. So when you derive the Hawking radiation and calculate what is the, the power spectrum of a scalar field and things like that, exactly same thing arises. This sign, instead of becoming sine, it becomes sine hyperbolic, and due to that sine hyperbolic, you get the Planckian distribution that you have in Hawking radiation, right? So physics is not very disjoint. I mean, gravitational wave and Hawking radiation does go hand in hand. Yeah, there are many examples like the gray body factor, which is very well known in Hawking radiation. People are now using it in gravitational wave in order to study stability of objects. So yeah, whatever you learn has some use. So anyway, so putting it back, I mean, I'm not going to do any further, but this is all that I have. Then there is gamma 1 plus L plus 2I omega m, and gamma minus 1 minus 2L, if I replace, then I will have sine of, okay, let me not do this because I'm not interested. So first of all, if I taking the ratio of these two, because that's what it appears, you see gamma minus 1 minus 2L divided by gamma 2 minus L, that ratio will have sine minus pi plus pi L and sine 2 pi plus 2 pi L. So what is sine 2 pi plus 2 pi L? Sine 2 pi L. And sine minus pi plus pi L? Whatever, minus or plus sine pi L. Now sine 2 pi L is 2 sine pi L cos pi L. So the sine pi L cancels and you are left with cos pi L. Now cos pi L is a finite quantity when L becomes integer. So therefore your divergence goes away and you get a finite answer. Correct? So you get finite, but whether it is real or imaginary is actually decided by the ratio of these two terms. So here also, if you play exactly the same game, then you can show that this ratio would be some function of L. Then it would be gamma 1 plus L plus 2I m omega, then gamma 1 plus L minus 2I m omega, sorry, and then you will have pi and multiplied, that will be on the top, sine of pi L plus 2 pi I m omega. So what I have done, I have just written this gamma using this formula. So this is Z, so 1 minus Z would be 1 plus L minus 2 I m omega, which is here, and then you will have sine with some factor of pi L and then 2 pi I m omega. These two multiplication is something that is there, even in Wikipedia you can find it. It is gamma of A plus IB times gamma of A minus IB, which you can write in terms of there is a multiplication of K square plus B square and so on and so on. But this is not of our importance. The important term is this. So this term, I said m omega I have assumed to be small. So what is this term? Sine pi L, L is integer. So it is sine of 2 pi I m omega, which is I m omega, because sine, if you multiply, I mean sine x is x, right? So that means you have some function of L, then you have this gamma function multiplied times you have I into m into omega, correct? And what I said is the tidal love number is the real part of it. What is real part of I omega? 0. So therefore the tidal love number of Kerr black hole is also 0 in the static limit. But there are some caveats, because if you add time dependence or frequency dependence, there would be additional pieces over there. This is done under some approximation which is not 100% correct. If you add them, then you find that the static tidal love number is indeed 0. So, all the results that people get are consistent. But if you include frequency dependence, then you can have non-zero love number. For example, for a Kerr black hole, you will have a term which is like rotation into m into omega. So, this a is the rotation parameter, m you remember e to the im phi, that m, and then omega is the frequency. So, if you put a equal to 0, it goes away. So, that means non-rotating black holes even in dynamical situation does not have a tidal love number, but rotating black holes do have a non-zero tidal love number. Okay, so these results, I mean, I think you can easily understand how it comes. It effectively expansion of the hypergeometric function. Black hole perturbation theory in the rotating case is all about solving hypergeometric differential equations. So, whatever you do, you will get some sort of hypergeometric equation, and then you have to deal with its various limits in order to get the answer. And it is inevitably gamma functions. So, you have to deal with that identity no matter you like it or not. Fine. So, I think it is past 7. So, I will stop here with the tidal love number. The tidal heating I will finish tomorrow, and some discussion on environments. Okay. So, thank you for being here so late in night.